Hello and welcome to lesson number 27, Permutations and Combinations. These two allow us to find lots of different things, like the different number of ways which we can arrange certain elements within a list, the different number of possible ways that we could choose elements to make a subset of a bigger set of a list, and the different number of ways in which a certain event could occur, leading to the probability of an event occurring in a specific way or some general way, and many more different applications. To start off with this lesson, we need to talk about something which is very fundamental, and due to that it's known as the fundamental principle of counting. The fundamental principle of counting states that if you have two events, which I'm going to call, let's say, event A and event B, if you have two events A and B and they are independent of each other, meaning that the outcome of A does not affect the outcome of B. If there are m number of ways that event A could occur and there are n number of ways that event B could occur, then the total different possible ways that A and B could occur together are m times n. This can be illustrated with something like, let's say, a two-digit number. If you consider a two-digit number like this, let's consider this box to represent the first digit, and let's consider this box to represent the second digit. The number of possible choices for the first digit are going to be all the choices from 0 up to 9. So 0 to 9 is 0, 1, 2, 3, 4, 5 and so on, which is 10 total choices. The different number of choices for the first box is 10. As for the second box, again, since we're choosing a digit, the different number of choices is going to be 0, 1, 2, 3, 4, 5 and so on up to 9, which gives us a total of 10 total choices. So the number of choices for the second box is 10. Now, if we consider the total number of numbers that we could create from these two digits, since this digit is independent of this digit, the total number of numbers we can create is 10 times 10, which is going to be 100. These 100 numbers that we could create from these 10 digits are the digits starting from 0, 0, and then 0, 1, 0, 2, 0, 3, and so on, all the way up to 99. So the numbers from 0 to 99 are the 100 numbers that I'm claiming to be produced from these two digits. Importantly, this illustrates the fundamental theorem of counting, which shows us that 10 options for the first thing and 10 options for the second thing, provided they are independent, gives us 100 total possibilities for the total event. Now that we established that, we can move on to our very first concept, which is going to be what permutations are. In mathematics, a permutation just refers to a specific arrangement of the elements within a set. So let's suppose a set S is going to be the set, let's say, A and B and C. Now right now it might look like A, B, C are in an order within this set. However, if I instead of this draw this set as being S, which is in like a Venn diagram fashion, A, B, C like this, now you can't really say that they are in any order. This is actually how this set appears currently. This set is an unordered set. If we consider taking the elements of this set and arranging them in some specific order, then what we are producing is a permutation of the set S. For example, the specific order A, B, C is a certain permutation of the set S. Another possible permutation could be B, A, C. Another possible permutation would be C, A, B. Another one would be C, B, A. Another one would be A, C, B, and the final possible one is going to be B, C, A. These are the 6 total possible combinations that we could have as in the different permutations of the set S. So here you can see all of these permutations are unique from each other. A, B, C is only appearing in this thing here. It does not appear in the rest of the permutations and neither do any of the others. For our purposes, we're going to assume that all the elements of a set are unique from each other. Because if they weren't unique, we could potentially have duplicates. For example, if instead of a B and C here, let's suppose that this B was also an A. So I'm going to write above it just an A temporarily. If this B was also an A, then all of these would be replaced by this thing would be A here, this thing would be A here, and this thing would be A here, this thing would be A here, and so on. So here we can see, if we just consider the first two, this would be AAC. The second one would also be AAC. So here we can see that if we allow duplicate items, we could have multiple permutations corresponding to the same exact order. Because of this, we avoid this by assuming that all of our elements within our set are unique from each other, and therefore any permutation of the set is going to be unique from any other possible permutation of the set. So now, given that rule, let's try and establish a way that we could calculate the total number of permutations that we can create for a set, because that turns out to be quite useful when we're dealing with probabilities of different sets and other things like that. So here we can see for this set of size 3, we have a total number of permutations of 6. Let's, instead of this, consider a random set of size n. So I'm going to represent it with a circle like we did earlier. This set S is going to be represented by this big circle here, which has n total elements within. So I'm going to represent that with an n on the outside like this. So let's suppose these n elements go like, let's say A, B, C, a bunch of others in the middle which are not important, and then the last elements are X, Y, and Z. So I know when I say last element is kind of introducing an artificial order, but there's no order here. Let's assume that all of these are just randomly just there. They are not ordered in a specific way. So now, given these n total items, what I want to do is to arrange them in a specific order. And given that, I want to figure out how many total possible orders are there that I could arrange these n total items in. So first off, let's consider how we're going to order them. We could order them in different arbitrary ways, but for our purposes, the easiest thing is going to be ordering them into a straight line. So what I'm going to do is to draw a straight line like this and consider ordering them from, let's say, left to right. So the leftmost one is going to be the very first element, and then we have the second element, the third element, and so on all the way down until we get to the one that's 2 before the last element, the one that's 1 before the last element, and the very last element. So here we have a total of n total elements, and we are arranging them in this straight line form of order. So let's consider how many different ways that we could do this total arrangement, as in how many different possible arrangements are there that are unique from each other. For this purpose, again, I'm going to reiterate the point that each of these elements, this n number of elements within the set S, are all unique from each other. Now, if we consider the total set as it is currently, there are n total elements within the set. If we consider choosing one of them to go into the first box, how many choices do we have? Well, if there's n total elements and any one of them could go into the first box, then there must be n number of choices for the first box. But now suppose we make that choice. If we make that choice, then that element, whichever element we put into the first box, is no longer an option for any of the other boxes, because now it's already been selected. It does not appear twice within the set S, so therefore it cannot appear twice within any particular arrangement of the elements of the set S. So let's suppose that this element that we put here is C. Then C is now no longer an option for any of the other different positions within this line arrangement that we're doing, because we established previously that C is unique. So if C appears once in any permutation of the set S, it cannot appear again. So now, if we no longer have the option of C for any of these boxes, then for the next box, this box here, if we consider total number of options that we have, we used to have n total number of options, but now we eliminated one, which means now we have only n minus 1 total options for the next box. So considering that, the number of different options that we have for the next box is going to be n minus 1. Let's suppose for this box we choose the option A. So now A is also gone. Again, since A is unique, A cannot reappear in any of these selections. So therefore, A is also no longer an option for the rest of the boxes. So now considering this, once again applying the same principle, we've now lost 2 elements from our original set because they are no longer available for the rest of the boxes. One of them has been gone into the first box, and one of them from the remaining has been sent to the second box. So considering the third box, we used to have n total items, now 2 of them are gone. So the number of choices we have for the third box is n minus 2. Let's say we put B to that one. Now that one's gone. If we consider the next box here would have n minus 3 total choices, since 3 of the items have already been chosen. The next box after that would have n minus 4 choices, and then n minus 5 choices, and so on downward. Now, let's skip ahead and consider the very last choice. For the very last choice, we're assuming that we've already made n minus 1 number of choices. All of the boxes before that have already been chosen and given a certain element from the set S. Now if the set S has n total number of items and we've already chosen n minus 1 number of those items, then there must be only one item left over after making all of those choices. So using that logic, for the very last box, there could only be one total choice. Now, if we consider the box before that, for the box before that, we actually had two total choices. Since for the box right after it, since we've already taken one of the choices out, we're only left with one choice. So for the box before the last one, there are two total choices. For the box before that, there would have been three total choices. For the box before that, there would have been four total choices and so on all the way upward. So now we have that the very first box has n number of choices. Given that we make that choice, the next box has n minus 1 number of choices, the box after that has n minus 2 number of choices and so on, all the way down to 3 choices, 2 choices and 1 single choice. Now, here is where the fundamental principle of counting comes in. If we consider the first two boxes, the different number of ways that we could choose an element for the first box is n. When we do that, the different number of options that we choose for the second box is n minus 1. And this n minus 1 crucially is independent of what choice we choose for the first box. We could have chosen C for the first box, the number of choices for the second box would be n minus 1. We could have chosen A for the first box, it would still be n minus 1 and so on. So therefore, the number of choices that we make for the next box is independent from the previous box's number of choices. Due to this, the number of different ways that we could choose the first two boxes is going to be the product of the different number of ways we could choose for the first box and the number of ways we could choose for the second box. So therefore, the number of ways we could choose for the first two boxes is n times n minus 1. Now considering this and considering the third box, if we establish this thing as being a single event, as in choosing the first two is a single event, and we consider the next box after that, it doesn't matter which two elements we choose for the first two boxes, the next box after that will always have n minus 2 total options. And then if we consider that and we consider the total number of ways that we could establish the order of the first three boxes, we see that it must be n times n minus 1 times n minus 2. If we keep repeating this pattern considering the total number of ways that we could choose for the next box, we see that our total number of choices becomes n times n minus 1 times n minus 2 times the next one is going to be n minus 3 and so on all the way down to here, and we can see once we get to this point we have 3 number of choices for that next box and then 2 number of choices for the next box and 1 choice for the very last box. Again applying the same principle, the number of choices for the last two boxes is 1 times 2 and then 1 times 2 times 3 for the box before that and then that and so on. Which means if we consider the overall total number of arrangements, the different ways in which we could arrange all of these different elements into these n number of boxes is going to be n times n minus 1 times n minus 2 times n minus 3 all the way down to 3 times 2 times 1. This specific value that we have here actually has a special notation dedicated for it. What we have here is the product of all the integers, all the positive integers starting from n going down until 3 times 2 times 1. This is denoted as n factorial, as in n factorial is the product of n times n minus 1 times n minus 2 times n minus 3 all the way down to 3 times 2 times 1. N factorial is the product of all positive integers all the way down to 1. So given this, we can now see that if we use this notation, then the total number of ways in which we could permute a set of n total elements is simply n factorial. So then we can write down here for a set S of n total, and another important thing is that they are all unique from each other, so we can say unique items is going to be n factorial, as in if we have n total items and we shuffle them around, the different number of ways that we could shuffle those n total items is going to be n factorial. Applying a practical example to this, if you consider a deck of cards, a deck of cards has 52 total cards. These cards are divided into 4 different houses, each of which having 13 total cards, which is where we get the 52 from. So if we consider this deck of cards and we consider shuffling them, what we're essentially doing is considering the total different number of permutations or orders of the different cards. As in, we could think of them as like a stack. The top card is the first card, second, third, fourth and fifth and so on all the way downward until we get to the 52nd card, which is essentially what we did here. So given that logic, if we consider the total number of ways that we could arrange the cards, as in the total number of shuffles that these cards could have, the number becomes 52 factorial based on our formula. So therefore, considering a deck of cards, the different number of ways that we could shuffle these cards is going to be 52 factorial. So 52 factorial. 52 factorial is 52 times 51 times 50 times and so on all the way downward to 3 times 2 times 1. This number is incredibly large. If we approximate it, this number is approximately 8.066 times 10 to the power of 67. This number is so big that it's approximately the total number of atoms in the Milky Way galaxy. It's that big. Due to this, if you take a stack of cards and you randomly shuffle them, once you're done randomly shuffling, it is extremely likely that the certain orientation or the certain order of cards that you have at the end has never been seen by any human in the entirety of human history, because there's just that many different total number of combinations. So that's what we mean in mathematics when we say the total number of permutations of the total elements of a given set. What we're going to consider next is also related to permutations, however it's slightly different. See here, we were taking all of the elements of a given set and considering all the different permutations of them, as in arranging them in different orders and seeing how many different orders there were. What we're going to discuss next is, instead of taking all of the elements of a given set and arranging them in a certain order and calling it a permutation, arranging a certain subset of the given set in different orders. So instead of taking all n elements, we're going to take less than n elements. The number of elements we're going to take is going to be called R. So let's consider the situation. We have a base set of size n, it's going to be called S. So this set contains n total elements. I'm going to label a few A, B, C, D and so on. And from this set, we construct smaller sets, as in subsets. So let's say S prime is a subset, and these subsets that we construct are going to have only R elements. So we're randomly choosing a bunch of the elements from this big set that we're going to take into this set. We're not necessarily taking all of them, we're only taking R of the total n number of elements from our original set, and using that we're constructing a smaller set. So in this case, let's suppose we take A, B, maybe we take E, we don't take C and D, so clearly it's a subset of the set S, and given this certain arrangement of elements, we now try to figure out what are the total different permutations of this given subset S prime. And then we do it for the next possible subset and the next possible subset. What we want to find is, for all of the possible subsets, as in this subset here has A, B and E, we could have another possible subset of size R which instead of E contains C, and another one that doesn't have B but contains D or something like that. Adding up all of those, adding up all of the possible subsets of size R and all of the different permutations of each of those given sets, what we are trying to find is the total number of subset arrangements of length R that we could create from our original set S. So let's try and figure out how many that is. So considering our problem, we have an initial set of size n that is called S. So here we have n total elements, we'll call them A, B, C, D and so on. We want to construct a bunch of arrangements of these elements of this set that are each R elements long. So here we have R elements starting with the first element, second element, third element, so on and so forth until the last element, in that order from this set S. So if we consider this in the same method that we consider the total permutation, as in the total permutation of n items, if we consider in the same way the total permutation of R items instead of n items, for the first item we have a total of n total choices. It could be any of these elements. Again, remember, all of these elements are assumed to be unique for our purposes. So then, For the very first choice, in this case, we can choose from any one of the n total elements within the set S. So if we do that, we have n total choices for that first element. And now one of them is gone. Let's suppose we choose B for our first element, in which case B is gone. Now, for the next element in our ordering, we have only n minus 1 choices, since one of the choices is gone. So then, for this thing, we have n minus 1 choices. For the next one, we will have taken 2 of them out, in which case we will have n minus 2 total choices. So for the third option here, we will have n minus 2 total choices. Now observe, for the first choice we had n total choices, for the second choice we had n minus 1 total choices, for the third choice we had n minus 2 total choices. We can see we have the n, we have a minus, and the minus number is 1 less than this number of the number of the choice. So if we number these choices 1, 2, 3 and so on, the last choice will be the rth choice, the one before that will be the r minus 1th choice, the one before that will be r minus 2th choice. So given this, we can see that if the first choice is going to have n total choices, that is n minus 1 total choices, and the next one, n minus 2, is going to be n minus 1 is going to be n minus 2 minus 1. The next option here is going to be n minus 3 minus 1. Then for the final option, the final choice is going to have, according to our formula, n minus the number of the choice, which is r in this case, minus 1 total choices. So this last item here is going to have n minus r minus 1, or n plus 1 minus r total choices. So we have n plus 1 minus r, or I could write it as n minus r plus 1 total choices for this last item. Going backward, we can see that the next one will have n minus r plus 2 total choices, the next one before that will have n minus r plus 3 total choices, and so on. So now, considering this product, we have n times n minus 1 times n minus 2 is the exact same, is starting off the exact same as it had for the total n number of permutations, but in the n number of permutations, if we consider the total number of permutations, it ended at times 1, but for this one, it instead ends at n minus r plus 1. So, if we consider this thing right here, is there any way that we could simplify this and write it in a nicer way? As in, a nicer way in terms of, let's say, the factorial function. And as it turns out, there is a way. If you consider this expression and you consider what n factorial is n times n minus 1, same exact thing as here, times n minus 2 times and so on. It goes all the way down to n minus r plus 1, so n minus r plus 1, but then it keeps going. It goes to n minus r and then n minus r minus 1 and so on downward until we get to 3 times 2 times 1. Now if you consider this expression for n factorial and you consider the expression we are trying to go for, you can see that all the terms after the n minus r plus 1 are not there. As in, all of these terms do not exist in this expression for the total number of permutations of that subset. So, how do we get rid of this? Well, we can see all of these terms here are multiplied. So all we have to do is divide by that same number. So all we have to do to get the total number of permutations that we have here is simply divide by all of these terms, which is n minus r times n minus r minus 1 times ... all the way down to 3 times 2 times 1. Now notice, n minus r times n minus r minus 1 times n minus r minus 2 times all the way down to 3 times 2 times 1 is exactly the definition of n minus r factorial. It's the product of all the positive integers starting from n minus r all the way down to 3 times 2 times 1. Therefore, this expression here that we're dividing by is n minus r factorial. So we have to divide by n minus r factorial. And now, if we consider this expression on the right hand side, we can see by our division and multiplication we have cancelled out all of the unnecessary terms, leaving us with just the total number of permutations. So the total number of permutations, as in n times n minus 1 times n minus 2 so on all the way down to n minus r plus 1, is equal to n factorial divided by n minus r factorial. This has a special name. This thing right here, this expression n factorial divided by n minus r factorial, is called the permute function. It's written as n in superscript, capital P, r in subscript, npr or n permute r. It is n factorial divided by n minus r factorial. From our derivation of this function, we can see exactly what it means. If you have npr, what we are representing here is the total number of permutations of subsets of size r that could be created from a starting base set of size n. In order for this expression to be valid, we of course need r to be less than or equal to n, because if r is greater than n, then our original assumption doesn't make any sense, because here we can see if we added many terms like this and we eventually got to an nth term, as in r equals n, and if r was greater than n, we would have another term after this. The number of choices for the nth term would be 1 and the number of choices for the very next term would be 0, since by the time we've exhausted n total choices, we are out of elements in our original set S. So for this reason, r has to be a number that is less than or equal to the number of elements in the initial set, or n. So r is less than or equal to n. So given that, the meaning of npr is to find the total number of permutations of subsets of size r that could be created from an initial starting set of size n. For an example of us using this theory, we can consider something like, say, making a password. So let's say we make a password and we make it using the 26 letters of the English alphabet. So then our initial set S is going to be the set of 26 letters starting A, B, C, D and so on. So out of these 26 letters, let's suppose we want to make a password that is 10 letters long. So our final arrangement, our subset, is going to be 10 letters long. So given this, let's suppose, for the sake of using this formula, since we don't know how to deal with duplicates for now, that from these 26 letters, we take one letter at a time until we have 10 total letters in a row. As in, we don't have any duplicate letters. Within our password, we don't have 2 A's or 2 B's or something like that. So given that, what we're essentially doing is taking one element at a time from the set S to form a password which is 10 characters long from our initial set of 26 characters. So given this and our form for finding the NPR from earlier, we know that if we are taking a set S of 26 elements and turning it into subsets which are ordered and have 10 elements each, then the total number of subsets, the total number of ordered subsets I should say, that we can create from this initial set S is going to be the first number 26 permute 10. So therefore, the total number of passwords that we could make is 26 permute 10, which is going to be, according to our formula, 26 factorial divided by n minus r factorial is going to be 26 minus 10 factorial, as in 26 factorial divided by 16 factorial. This is a very big number. If you see, we have 26 factorial divided by 16 factorial, which is going to be 26 times 25 times 24 all the way down, divided by 16 times 15 times 14 all the way down. If we cancel out all the terms, what we're going to be left with is 26 times 25 times 24 times ... all the way down to the very last term, which is going to be 1 greater than this term on the denominator, so 17. This is the total number of passwords that we could make if we take one letter at a time from the total letters of the English alphabet, where we do not repeat letters. We'll learn how to repeat letters in the next video, but for now, we're just going to consider taking one letter at a time and making this password, in which case, this is the total number of passwords that we can make. You can see how the permute function is useful. In the next video, we're going to go over another function that is even more useful objectively, and it is called the choose function. However, for now that's going to be it for this video. Stay tuned for the next video. It should be coming up in the end card if I've uploaded it by this time. So that's going to be it for this video. Today we learned about permuting all the elements of a set and how many different such permutations are there. And then we learned about the permute function NPR, which instead considers making a smaller ordered set from a large set and considers how many different unique ordered sets we can make from that large set. So that's going to be all for this video. Thank you for watching and goodbye.